Hello, TAs for ATS 114. I want to help you take a look at a Lab 8, and we're just going to walk through the digital copy a little bit so I can help you with what some of this is going to be. The video for the students themselves actually turned out pretty good, and please do watch that before class because it has a lot of information that I think you're going to find helpful. Now, the beginning of this chapter, I mean, good grief, there's a whole lab. There's just one lab called atmospheric motion. I mean, there's lots of things that could be atmospheric motion in this class. We will not be able to do anywhere near this whole thing. It would probably take 3 weeks to get through the whole thing. So we're just going to focus on two of the forces that are causing atmospheric motion, namely the pressure gradient force and the Coriolis force. And then the lab manual has them talk about upper level winds and upper level winds in troughs and ridges and so on. We're going to focus just on surface winds just because that's something different than they did in the homework for the class. So the first thing they're going to talk about here is pressure gradient force, and they're going to have a map like this to work with. And the map says circle the area with the greatest pressure gradient. Okay, the pressure gradient is related to how close together the isobars are on the map. So an area with a good pressure, strong pressure gradient would be like, through here, well, especially like, I'm having a little hard time controlling it, but like right through here, I need to get a touch screen to make it, this would be an area where the pressure gradient is very, very strong, where the isobars are getting close together, because over a short distance, you are having a big change in pressure. Use arrows to show the direction of pressure gradient force at a few locations. Okay, we walked through that quite a bit in the lab, the discussion. The pressure gradient force vector should be a vector at any given location that points perpendicular to the isobars towards areas of low pressure, away from areas of high pressure, but perpendicular to the isobars at that location. So they should have something like this on there. And finally it says label a region where you would expect to have the lightest winds. The strength of the wind is determined by how close together the isobars are. So we want to find a place where the isobars are really far apart. This would be a great answer down here over this tropical Atlantic, something like that. Any place where the isobars are really far apart. Okay, do not do any of this stuff about optional mathematical treatment of the pressure gradient force. They've already done that in a homework activity. There's no reason for them to do it again. All right, then we take on the Coriolis force. Make sure you've watched this video about the Coriolis force that I've made for the students and read through all of this, because the Coriolis force is really a tricky concept. I mean, it's hard to teach that in like 500 level classes. They definitely need to understand this basics, though, that the Coriolis force deflects motions to the right in the northern hemisphere and to the left of the southern hemisphere, and the Coriolis force is going to be stronger the faster the motion is. So, for example, if I switch over here, this little activity is interesting. This is supposed to be like the Earth, looking at the Earth from above. So like here's the North Pole. And the activity tells them to put like a little object up here off of their desk, on their desk, and pivot the book around this North Pole in the direction of these arrows. They're first supposed to just draw a line straight to their little object up there before they rotate it. And then they're supposed to just pull their pencil across from north towards their little object while pivoting their pencil around that North Pole. You'll see it. I actually worked really hard to get the animation to work on the video that I made for the students. But if you just drag your pencil straight, but while turning the book, they get this curved line. The pencil went in a straight line, but the paper underneath it moved. This is not exactly how the Coriolis force works, but it's not a bad analogy. And so it's a good teaching point that, notice how from the point of view of the direction the object is moving, it's being deflected to the right, and this is the northern hemisphere. If they do the same little activity down here for the southern hemisphere, see the South Pole here? And also if you're looking, from below the globe up towards the South Pole, you see how the Earth is now rotating this way. So they do their little activity, they draw a little line towards their object before, and then they do it after they rotate the object with their help of their neighbor. They'll get a little curved path that way, and this will all work out. And that leads them to this idea that the textbook is doing here, where there's a set of these 4 plots. It's not quite clear because I can't get them side by side on here, but there's 4 of these plots. And again, I make it more clear in the student video, but this is like a time 1, this is over here a time 2, and then the other ones are a 3, and then finally a summary where you summarize the results. And you might not notice, but if you look at the 4 globes there, they're all positioned a little bit different. The Earth is rotating. North America is in a slightly different place on each of those 4 plots. And it's very, very hard to see, but there's like a little missile right here at the North Pole at time 1. And then that little missile is just a little ways away from the North Pole at time 2. And if you move over to time 3, it's a little farther. But the Earth is rotating under the missile. And so if they transfer those locations correctly onto this globe right here, what they're going to see is that the missile has taken kind of a curved path. Okay, the missile moved in a straight line, as they can see by comparing plot 1, plot 2, and plot 3, but the Earth turned underneath it. And so it's tracing kind of a curved path on the ground, even though the missile is in fact moving straight. Once they have that kind of tool in their toolkit, they can do the same thing on the next problem for the southern hemisphere, and they can do the same thing on these plots here, where they're going to be moving the missile farther every time step. And you'll find out that the deflection is larger. Now they're going to get, I don't know, something kind of like this. The deflection is farther to the right of what was the original straight motion of the missile. Because the Coriolis Force is stronger, the faster the motion is. Again, this is not exactly how the Coriolis Force works, but it's a good analogy for how the Coriolis Force works. And, it leads to the correct understanding of how things are going on. Do not do any of this stuff about the vertical component of the Coriolis Force. That is way too complicated. Any of this stuff, all right. Any of this stuff about upper level winds, again, it's not that it's unimportant or anything. It's just that we can't do everything, and let's focus on things we can get done in one particular day. Gradient wind, if I had time, I would love to do this. This might make a lovely activity in some other course, but not in ATS 114. And don't do any of this stuff on the left side of page 96. So we're going to continue then over here at question 25. Sorry, this interface here on the digital edition is hard to control. We're starting back up then at question 25. What effect will friction have on the surface wind speed, and what effect will a reduction of surface wind speed have on Coriolis Force? Well, earlier in the lab, they determined that wind speed is related to Coriolis Force. The faster the wind is, the stronger it is. So therefore, by reducing the wind speed due to friction, you're going to have reduced the strength of the Coriolis Force. Question 26. Watch the online video, the video that I've made for the students, and you'll understand that there's a lot of problems with this figure here. If they had given more information up here, this is a simple question, the students will understand a lot better once they've seen the video that this is a map, that these are isobars on the map. There's an area of low pressure to the north here and an area of higher pressure to the south down here, that this is an air parcel that is moving in this direction. Once they have all that information, this problem is not so hard to work with. All it's asking them to do is to draw the pressure gradient force. Well, the pressure gradient force should always be perpendicular to contours from high pressure towards low pressure. It asks them to draw the Coriolis Force. The Coriolis Force is always 90 degrees to the right of whatever the motion is. And friction should always be in the opposite direction of what the force, the motion is. So as long as they've been walked through on my video what all these things are on this diagram, that takes seconds to actually put the vectors on there. They just can't figure it out from the instructions there. Now, based on that, this is a neat activity what they do here on page 97, but they need some help with this. Okay, these are supposed to be cyclones or anticyclones, but they don't have H's and L's in the middle. They don't have areas of, they're not telling them whether it's areas of high pressure or areas of low pressure, and it's not telling them whether they're in the northern hemisphere or the southern hemisphere. It's interesting, but it is a very challenge. The trick to notice is after I've given them the lecture, cyclones are the ones where the winds spiral in, and anticyclones are the ones where the winds are spiraling out. So once they notice, the trick here is to notice first whether the winds are spiraling in or spiraling out. So you notice how in their instructions it says, tell us whether this is in the northern or the southern hemisphere, and tell us whether northern or the southern hemisphere, and tell us whether it's a high pressure or low pressure. Do the high pressure or low pressure first. See, if the winds are spiraling in, this is a low. This is an area of low pressure. If the winds are spiraling out, this is an anticyclone. It's an area of high pressure. So like here, this one, the winds are spiraling in, it's got to be a low. And this one here where the winds are spiraling out, it's got to be a high. Okay. Now, once they know whether they're a low or they're a high, well then they can use their knowledge about which way highs and lows rotate in which hemisphere to say, oh, these are winds spiraling in, it's a low pressure system, and they're rotating counterclockwise. That's the way cyclones work in the northern hemisphere. So this one is north. And so on all through this activity. All right, we don't do anything associated with this. And in fact, I want them to read through this stuff about winds and vertical motion, but There's only one question here that they do. All right, it's just basically explaining how as air converges at the center of this cyclone, it has to rise. There's no place for it to go but up. Same as air diverges away from the center of this anticyclone, air from a loft has to sink down into the center of that anticyclone to take the air's place. Of the review questions, the only one that's really appropriate, because it isn't one of the things that we skipped, is question 4. And question 4 is very closely related, actually, to the question they did at the top of the page. They won't have any trouble. If anything, they'll be confused as to why the two questions are so similar. Okay, I think this is a fairly appropriate amount of material. I look forward to hearing if it turns out to be too much or whatever. I look forward to seeing you guys on Tuesday. This has been Dr. John Shruggy.